intrinsic semiconductors. Welcome to Decreations Resources. So there are two types of semiconductors, namely intrinsic semiconductors and extrinsic semiconductors. So let's first try to understand what exactly are intrinsic semiconductors. Now consider an ideal semiconductor. That means it has no lattice defects. So all the atoms are existing at right places, which are basically defined by lattice rules, and that there is no impurity. So the ideal situation. So that basically is a situation where you will say that the semiconductor is an intrinsic semiconductor. So you can think of silicon with no impurity. It can be called as intrinsic semiconductor in that case. Now, when the temperature is 0 Kelvin, valence band is filled with electrons and conduction band is completely empty. As the temperature starts increasing, some of the valence bonds will be broken, and as a result, electrons will become free. And in this process, the thermally excited electrons get enough energy. Now, when you say enough energy, basically you are thinking of energy in terms of the band gap. Because if the electrons have to move from valence band to conduction band, they have to have energy more than the band gap energy, because that's basically the energy difference between the two bands. So if they get enough energy, then they can go to conduction band. So if the energy is more than band gap energy, they can go to conduction band. And when the electrons will go to conduction band, obviously they will leave behind a vacant space where in the valence band. So the excited electron has gone to conduction band and it has left a vacant space in the valence band. Now the vacant space is one of the electronic states in the valence band that can be occupied by another electron. So since there's a vacancy, another electron can come there. And this vacant space is referred to as a hole. So when we say there are two carriers, electrons and holes, this is the concept of hole. Now the excited electron in conduction band and corresponding hole in valence band. So it's a pair, electron hole pair. The excited electron in the conduction band has many states to move around. Remember, this was not possible at 0 Kelvin, since there were no electrons in conduction band and the valence band was completely filled. But now the electron has gone to the conduction band, and so it can contribute to conduction of current in electric field, under the influence of electric field, so as to say. Now similarly, there is a hole in valence band now that can also move and conduct current. Obviously the movement of hole, so when you actually say the movement of hole, you can understand that it's electron which is filling the vacancy. So indirectly it is as if the vacancy is moving, but we obviously understand that a vacant position can't move on its own. But since different electrons are occupying these holes, so when they shift, a hole is created in their place, so we call it as movement of holes. That's all. Now this movement of hole is opposite to that of movement of electrons, in the sense that one electron moving from left to right, we say it is equivalent to one hole moving from right to left. So here it is as if hole is a charged particle with charge equal and opposite to electron charge. Now we have understood that in intrinsic semiconductors, electrons and holes are created in pairs. So what can you comment about their concentration? Concentration of electrons and holes, when I say concentration, of course I am talking about the number per volume. So if we are talking in the centimeter scale, number per centimeter cube. So the concentration of electrons and holes at any given time or temperature has to be equal because they are generated simultaneously. So usually Ni is how it is denoted. So if we say that N is the number of electrons and P is the number of holes, we will say N is equal to P is equal to Ni. And this Ni is usually called as intrinsic carrier concentration. So it is a property of the material and it's going to depend on the band gap, because the generation of electrons and holes essentially depends on the band gap. Now, if the band gap is larger, what is your guess? Will Ni be smaller or will Ni be larger? Well, obviously, if the band gap is larger, Ni will be smaller. Since for a large band gap semiconductor, more energy will be required to excite an electron from the valence band to the conduction band. Now, typically, if you consider silicon, the intrinsic carrier concentration is 1.5 into 10 raised to 10 per centimeter cube. While if you consider a compound semiconductor such as gallium arsenide, the intrinsic concentration is 2 into 10 raised to 6 per centimeter cube.